Hello, so in today's video, we're going to find the derivative of the function, the modulus of x to the power of the modulus of x. So I guess the key thing to start off with this is to realize that this function is not defined for x equal to 0. I mean, that's because, well, when you do 0 to the power 0, that's not a defined quantity, really. There's no real definition of that or consensus on what that is. And also, I mean, when you differentiate this modulus to the modulus function, you're kind of going to get a pointy bit on the graph. So the graph of this function kind of looks something like, it kind of looks something like that. It's like a little point there at the number 1. So even though it kind of looks like it touches the number 1, we can't be certain that it does, because 0 to the power of 0, there's no definitive answer for that expression there. So yeah, so we know that we can't have a derivative at x equals 0. So yeah, let's go on with the differentiation. So again, this is kind of going to be a chain rule example. So when we differentiate this function, we know that we can rewrite this function as follows. So the exponential function with this natural logarithm of the modulus of x inside that multiplied by x. Sorry, the modulus of x there should be. Okay, so we've got that. And then now again, we can just use the chain rule here. So this is going to be the derivative of this e to the ln modulus of x multiplied by the modulus of x with respect to the natural logarithm of the modulus of x multiplied by the modulus of x, like that. And then we're going to multiply that by the derivative of the natural logarithm of the modulus of x multiplied by the modulus of x with respect to the variable x. Okay, great. So yeah, this first bit here, and again, this is just by using the chain rule. So with this first part here, this first derivative, I mean, this is just going to be e to the ln modulus of x multiplied by the modulus of x. And that's because when you differentiate the exponential function of a variable with respect to any variable, you get the exponential function of that variable. We know that from a previous video. And if we differentiate this second bit, so yeah, this is going to be the product rule. So we want to differentiate the ln mod x function with respect to x and multiply that by the mod of x, and then plus the derivative of this modulus of x with respect to x and multiply that by the natural logarithm of the modulus of x, like so. Okay, great. So now we need to use we need to work out those two derivatives inside the brackets there. So we know from a previous video that when we differentiate, when we differentiate ln of just x without the modulus, we get 1 over x, and it's the same result as when we when we differentiate this ln of modulus x, we get exactly the same result, which is 1 over x. So we did this in a previous video, this result there. And then when we differentiate this modulus of x, so differentiating modulus of x, so yeah, so the result we got for this was modulus of x divided by x, like so. So we got those two key results there, which we can just plug into the formula down there. So we're going to get e to the ln modulus x multiplied by modulus x, and then multiplied by, so the derivative of ln of modulus of x. So that's going to be 1 over x multiplied by the modulus of x, and then plus the derivative of this modulus of x, which we know is the modulus of x over x, like so, and then multiply that by this ln of x there, sorry, ln of modulus of x, ln of mod x, like so. Great. And then we can just simplify this a little bit. So we've got e to the ln modulus of x, but exponential functions and natural logarithm functions are inverse functions. So this is going to be the modulus of x to the power of the modulus of x. And then multiplied by this thing here. So we've got the modulus of x over x, like that. And then plus the modulus of x over x multiplied by the natural log of the modulus of x, like that. So then, yeah, we get that result down here. So let's just write this on a new slide. So the derivative with respect to x of mod x to the power of mod x is going to give us, so mod x to the power of modulus of x multiplied by the modulus of x over x plus modulus of x over x times the natural logarithm of the modulus of x, like that. And then what we can do actually is just factor out this modulus of x over x. So we get modulus of x over x multiplied by modulus of x to the power of modulus of x multiplied by 1 plus the natural log of the modulus of x, like so. And then what we can actually do now is, well, we've got a modulus of x multiplied by a modulus of x to the power of a modulus of x. So using rules from indices, this is just going to be the modulus of x to the power of the modulus of x plus 1, and divide that by x like that. And just to spell this out, so modulus of x to the power of 1 multiplied by modulus of x to the power of modulus x. You add the powers using indices laws to get 1 plus modulus of x there. So that's just what I'm using up that bit there. And then, yeah, to simplify the rest of it, so yeah, we're going to get 1 plus the natural logarithm of the modulus of x like that. And so, yeah, that's actually our final result. And just to remind ourselves, so yeah, this derivative is not defined clearly for when x is equal to 0, because you can't have a defined result there. But actually for any other values of x, so even negative values, positive values, whatever real values you like, this derivative is defined because the natural log of a positive number is defined. And obviously a positive number to the power of a positive number is also defined too. So yeah, so this is all fine apart from at x equal to 0. So yeah, that's the result in this video.